Hi everybody, today we'll talk about a specific example of computing Galois groups over Q. In particular, Galois groups of so-called palindromic sextics. Okay, let's start. So suppose we have a polynomial fx with integer coefficients. Say it is monic. Separable, and let's say of degree n, and the goal is to compute its Galois group. More specifically, let's K be its splitting field over Q, and let's GF be the Galois group of K over Q. Okay. Now we know one thing. Since GF acts on the set of roots of F, on the set of roots of F, and F is separable, so it has n distinct roots, we can visualize GF as a subgroup of the symmetric group Sn. Right, and in general, the goal at this point is, given a polynomial f, can we really compute which subgroup it is? In general, it's not a very direct, easy problem in terms of, I mean, it's not so easy to find one quick algorithm that takes care of it. But we already know some techniques for computing GF. So these were outlined in lecture notes of May 29th and June 5th. So let me go over some of these basic techniques. These were already discussed in the lecture notes. One thing to look at is cycle type. Okay, look at the irreducible decomposition of f. So say f is equal to f1 times f2 times up to fk, where the fi's are irreducible. And let's specify their degrees. Let's say degree of fi is ni. Now, if we know this decomposition, this immediately tells us something. Then G sub f is a subgroup of S sub n1 cross S sub n2 all the way to S sub nk, and that greater restricts it. Furthermore, if you intersect GF with any of these components, S and I, this must be a transitive subgroup of S sub ni. And of particular importance is when f itself is irreducible. Then, of course, k about is 1. So this tells us that G sub f is a transitive subgroup of S sub n itself. So this provides some economy because not all subgroups are transitive, and so you just have to look at those which are transitive. Okay, so this is the first thing maybe to look at. Okay, the next thing one could look at is the discriminant. Okay, so suppose alpha 1 up to alpha n are the roots of the polynomial f. We know they're distinct because f was chosen to be separable. Now, d or df, let's say, the discriminant of f is the product of alpha I minus alpha j squares for I less than j. Okay, I mean, we have some fixed order, right? So of the roots, it doesn't matter which one. But according to this ordering, look at all alpha I minus alpha j, square them up. Well, since you're squaring them, the ordering will not matter eventually. But so this is the discriminant of f. Since we started with an integer coefficient polynomial, we can say more. So it can be also computed by the formula d sub f equals minus 1 to the power n times n minus 1 over 2 times the resultant of f and its derivative. So here R is resultant. We talked about this in lecture notes. And in particular, this tells you that if you have an integer polynomial, the result will be an integer. Okay, so then the relation to the Galois group is, so d is a square, df is a square in Q or in Z for that matter, if and only if the Galois group of f is contained in the alternating group. Okay, so this is again one major thing that simplifies life, because discriminant is relatively easy to compute and checking that it's square is again relatively easy. Therefore, this provides some restrictions. Okay. Now, the other thing we also talked about is mod p reduction. So for this purpose, choose a prime p such that p does not divide the discriminant of f. Okay, now one thing we can do with an integer coefficient polynomial is reduce all the coefficients modulo p. So let's f bar denote the polynomial obtained from f by reducing all coefficients modulo p. So the resulting polynomial will be in fpx, okay? And, well, okay, I didn't write it here, but, okay, let's f be monic and irreducible to start with. Even if it is irreducible, once you reduce mod p, it may not stay irreducible. So suppose it decomposes in this way. suppose this is the irreducible decomposition in the space field. If this happens, then an important theorem of Dedekind, and maybe also attributed to Kronecker, says that GF must contain a permutation of cycle type given by the degrees of these Fi bars. So here, of course, Ni is the degree of Fi bar. Okay, now this last result is very powerful, but only in one direction. So but only in one direction. Namely, it tells you the existence of cycles of a certain type in the group, but you can only use this in this way, at least in this format, to prove that GF is large. So either the whole symmetric group or the whole alternating group or something like that. So if for some reason your polynomial doesn't have a large Galois group, you will not be able to prove anything in this way. You might guess the Galois group, but you still need some other method to prove that it is small. Okay, so in this lecture we want to sort of move in the opposite direction. So we'll look at some case study where we can make some deductions that GF is small by using some other tricks or techniques. Okay, so let's start over. So say f in Zx is irreducible, monic, and let's concentrate specifically on degree 6, so sextics. Well, we looked at cubics, quartics, and quintics in quite detail, so this might be some next interesting case. Okay, since the polynomial is irreducible, G sub f will be a transitive subgroup of S sub 6. Okay. Now, you might ask, what are the transitive subgroups of S6, symmetric group on 6 letters? So it turns out that there are 16 such groups up to isomorphism. So this is a little bit more crowded than what we have seen before. Well, in degree 3 there were only 2, in degree 4 there's a small list again, and degree 5 there are 5 such subgroups, but in degree 6 it suddenly jumps all the way up to 16. Now I'll give a reference for it and show some table from that reference. So the reference is the book by Dixon and Mortimer, permutation groups, page 60, table 2.1. But let me also show this to you on screen. Okay, here it is. So this table contains not just degree 6, but degree 4, 5, 6, and 7. That means subgroups of symmetric group on 4 letters, 5 letters, 6 letters, and 7 letters. So the ones that are labeled degree 6 are subgroups of S6. You only see 14 of them here, labeled from T61 up to T614. There are 2 more, but since they are kind of obvious, they were not written here. They are S6 and A6. So together with those 2 groups, you get the full list of transitive subgroups of S6 up to isomorphism. Okay. Now, I might come back to this table later. Okay, now a generic, so-called, it might be difficult to pinpoint what generic means, but a generic irreducible sextic has G sub f isomorphic to the full symmetric group. We kind of know that from before. It may not be too hard to construct something with group A6. Just, I mean, try to choose a polynomial as random as possible, whatever that means, but in a way that the discriminant is a square. Okay, I mean, most likely you'll get A6. It's also, well, let me say it is easy to construct F with GF isomorphic to A6, or also one other easy case is the cyclic group. For this last one, well, the reason is we know examples. I mean, you could take F to be phi 7x, for example, cyclotomic polynomial. Okay, but what about the other ones? So how would you get examples for the other groups, especially the small ones, which are not abelian? So some inverse problem maybe is in order. So given a transitive subgroup G, of S6, can we find F such that GF is isomorphic to G? How would you produce examples? That's the problem I want to address. So we should somehow pick some special F, right? So I mean, so that its roots have some certain symmetry. Well, the ultimate example is maybe the cyclotomic polynomial, where the roots, lie on the unit circle. But you know, that's one thing. But maybe to catch the other groups, you could do something else. Now, I want to do some specific example of that. I mean, which is kind of new. So let's look at so-called palindromic polynomials for that purpose. So what's a palindromic polynomial? This is not necessarily for degree 6, it can be in n degree. So suppose you have some polynomial here. It is called palindromic if, well, an is 1, an minus 1 is a1, an minus 2 is a2, and so forth. So, well, the leftmost coefficient is equal to the rightmost, the next one is equal to the next one to the right, and so forth. So there's the symmetry centered at the middle. So if you read forward or backwards, the coefficients, you get the same list. Okay, as an example, this particular polynomial x to the 4 plus 7x cubed plus 5x squared plus 7x plus 1 is palindromic. The first coefficient is equal to the last one, the next is equal to here, and 5 has no condition on it, so that's fine. So in general, a palindromic sextic would look like fx equals x to the 6 plus ax to the 5 bx to the 4 cx cubed, then go back to bx squared ax and 1. Now I want it to be an integer coefficient polynomial, so it is really specified by, so to say, 3 integers a, b, c. So some naive question, what is the Galois group of such a polynomial? I mean, can you figure out what the Galois group will be like in terms of a, b, c? Well, first of all, do we have any reason to believe that it's not going to be the full symmetric group? I mean, is this really non-generic in that sense? Okay, so let's prove some simple lemma about such polynomials. Okay, say f is palindromic. Now, if alpha is a root of f, then 1 over alpha is also a root. This is very simple to prove. You just plug in 1 over alpha. So I mean, this is true regardless of degree, but let me do in the sextic case. So you start from 1 over alpha to the 6th plus a over alpha to the 5 plus so forth plus a over alpha plus 1. But what you get here is nothing but 1 over alpha to the 6th times f alpha, therefore it's also 0. So this proves the lemma. Now, okay, can alpha be equal to 1 over alpha? Well, that only happens in 2 cases, right? So if alpha is plus 1 or minus 1. But if 1 or minus 1 is a root, then f cannot be irreducible. So if we assume f to be irreducible as well, then plus 1 and minus 1 are not roots. So the roots of f occur in pairs. So pairs like alpha alpha inverse, right? So in the case of sextics, f will have 3 pairs of inverse roots. Such roots. So these will be, let's say, alpha, beta, gamma, and alpha inverse, beta inverse, gamma inverse. These are all distinct, so you have 6 such roots. Well, let's say this is alpha 1 up to alpha 6 in some order that I don't know. Okay? Fine. Now, let's turn to the Galois group. So, say sigma is a permutation from GF, right? Now, if sigma sends one of these roots, alpha I to alpha j, well, I don't know which one, but you know, it could be any of them for now. But one thing is certain, sigma of alpha I inverse must be equal to alpha j inverse, right? Because sigma is an automorphism. So this immediately puts certain restrictions on G sub f. Why? For instance, its order. Let's see. Suppose alpha, beta, and gamma here are 1, 2, 3. So let's try to write a permutation 1, 2, 3, 4, 5, 6. Without loss of generality, let's say these are alpha, beta, gamma, and then these are alpha inverse, beta inverse, and gamma inverse. Let me try to write the rest of the permutation. So this is sigma. Now suppose that 1 is sent to something, let's say A. I don't know which one, but how many choices do we have? We have 6 choices here. Okay, well, immediately 4 will be sent to A inverse, which is another thing. So 2 of them are already occupied. So for 2, you don't have 5 choices anymore, you have 4 choices left. And then once you specify what this B is, then 5 should go to B inverse. And for 3, you have 2 choices left. And then 6 will automatically go to C inverse. So that will be what your permutations look like. And therefore, the total number of elements in this group must be less than or equal to 6 times 4 times 2, which is 48, right? So this immediately rules out some of the transitive subgroups. Let's look up in the list once again. So, okay, here is the list. Now look at these T6. Well, first of all, symmetric group and alternating group are gone because S6 has 720 elements and A6 has half of that, so 360, which are way more than 48. So those cannot be. And also in this list there are some quite big groups. So this one is 40. That's fine. Then if you go down to T6.9, that has 72 elements, so that's out. So, I mean, that cannot be. Likewise, the ones below 613 and 614 have too many elements, so again they cannot be Galois groups. So altogether 5 possibilities are eliminated. Okay. So this eliminates five of the 16 possibilities. Okay, this is very crude restriction, and we can do more. Let's see. Let's try to successively be a little bit more sophisticated here. So here's a small lemma again, saying that if f is palindromic, then G sub f cannot contain a 3 cycle. So 3 cycle, that means taking A to B, B to C, and C back to A, and doesn't move any other elements. So this is not allowed. So let's see why. So let's argue by contradiction. Suppose it does. So say sigma is in GF, where sigma is of the following form: alpha I, alpha J, alpha K. So some 3 cycle like this. And so sigma doesn't move any other elements than alpha I, alpha J, alpha K, and moves these in a cyclic way. Now, since sigma of alpha I is equal to alpha J, we must have, by this palindromic property, sigma of alpha I inverse is equal to alpha J inverse. Now alpha I is not equal to alpha J. This is an honest 3 cycle. Therefore alpha I inverse is not equal to alpha J inverse. In particular, alpha I inverse is moved, right? But here we have the list of all the things that are moved. There are these 3. So alpha I inverse must be equal to one of these. Well, it cannot be equal to alpha I. The inverses are distinct from the roots themselves. So it must be one of alpha J or alpha K. Is alpha J or alpha K. But these are both quite bad, because if alpha I inverse is equal to alpha J, then see what happens. Sigma of alpha I is equal to alpha I inverse, but then sigma of alpha I inverse should be alpha I back, but it's not, right? Sigma of alpha J is alpha K, so this is different from alpha K. This is a contradiction. Likewise, if alpha I inverse is equal to alpha K, that causes a contradiction in a similar way, because then sigma of alpha K is alpha I back. But then if this holds, sigma of alpha I should be alpha I inverse, but it is not, it is alpha J. Again, a contradiction. So the conclusion is that you get a contradiction in all cases, so that GF cannot contain a 3 cycle. So if we look up the list again, let me go back to the list, we can eliminate 3 more subgroups, not just because of order, but because of this particular cycle type. So on the right sides of this table, you see generators of the given group. So for example, if you look at T6.10, you'll see that there's a 3 cycle 1, 2, 3. So that group contains a 3 cycle. Likewise, 6.11 contains a 3 cycle, and 6.12 contains a 3 cycle. So now these are out of the game. So this eliminates three more subgroups, and we are left with 8 possibilities now. So 2 of these are contained in A6, you can check, and 6 are not. Okay. Now, then you can try to play with the integers a, b, c to see if these possibilities can be realized or not. For the rest of this lecture, I'll show that one of these possibilities can be realized at least. But as far as I'm aware, all of them can be realized by different choices, although I'm not 100% sure. So just as a demonstration, I want to show that one of these subgroups contained in A6 can be realized. Now let's look at the discriminant. Well, we use the formula df equals -1 to the power n minus 1 over 2, so 6 times 6 minus 1 over 2, resultant of f and f prime. Well, what I did is a direct computation by using Mathematica. I mean, it's maybe doable by hand, but it's a little bit large, so it's very quick with a calculator. So what turns out is this formula. So I kind of like the answer, so I'll write it down. You have such a factor times a much larger factor, but this second factor will be less relevant for us for reasons which will be clear. Okay, this is what Mathematica gave when I plugged in f and f prime to the determinant. Okay, it's rather complicated. Okay, whatever, but the point is there's a square on top. So, since we are chiefly interested in whether the discriminant is a square or not in Z, this second ugly factor will be completely irrelevant, and it all boils down to this much simpler part being a square or not. So, okay, so GF is contained in A6 if and only if DF is a square in Z, and that's if and only if this first part, this 2a plus c square minus 2b plus 2 square is a square in Z. And that's very easy to handle because this is a very simple thing. Now, it's like the difference of two squares being equal to a square, so it's very much like a Pythagorean triple. And there are many of these, you know. So you can choose your favorite Pythagorean triple and end up with something whose Galois group lies inside A6. So let's select one particular example. So let us select A equals 9, B equals 4, and C equals 8. I was not really careful about this choice. I just chose something that came to my mind. So then you can compute that 2a plus c square minus 2b plus 2 square is equal to 24 square. So it's a square now. And then you go back and compute the discriminant, again by some software, and it turns out to be 2 to the power 6, 3 to the power 2, and this quite large prime squared. Okay, that's what comes out. But the point is, it is a square. Okay. So our polynomial now is this one. is this palindromic polynomial. Okay. Well, you might ask if it is irreducible. It is. One can check. Let me see x. Okay. So you do get a transitive subgroup. Okay. Now, if we look back in the table again, we'll see that there are two possibilities left. So we see, I mean, out of these 8 remaining subgroups, only 2 were subgroups of A6. Let me not show it again, but let me write it here. These are the ones labeled T6.5. You could look up. Its order is 24, and generators 1, 2, 3, 4, 5, 6. Product of 2, 3 cycles. 1, 2 times 4, 5, product of 2 transpositions, another product of 2 transpositions, 1, 4, 2, 5. This is one possibility, and there's one more, T6.7, order 12, and generators 1, 2, 3, 4, 5, 6, and 1, 4, 2, 5. So this is like an index 2 subgroup here. It misses this extra element, right? So you have these two possibilities. Now we want to decide which one, okay? So you have this particular polynomial. Its Galois group is isomorphic either to this order 24 subgroup or order 12 subgroup, living in this huge group with 720 elements, right? So we were able to narrow down quite a bit, but which one of these two is it really isomorphic to? Now, we'll need one more bit of information to make this decision. So, but maybe some observations. So in these cycles, so 1, 2, 3, 4, 5, 6, so here, of course, this description of the subgroup doesn't immediately tell you which roots you are looking at in the Galois group, but remember what happened with the 3 cycles. If 1 and 2 here, for example, are an inverse pair of roots, that will immediately cause trouble because alpha will go to alpha inverse, but alpha inverse cannot go back to alpha, so that's quite bad. That doesn't happen in a transposition, that happens in a 3 cycle. So in this description, this 1, 2, 3 should be just alpha, beta, gamma in some order. And 4, 5, 6 should be alpha inverse, beta inverse, gamma inverse, maybe cyclically rotated. I don't know that, but I mean 1, 2, 3 should be choosing one from each pair, and 4, 5, 6 one from each other pair, the other element of these pairs. Okay, now to really make this final decision, which of these two groups is really the Galois group, we need one more observation. Which we could have done in the beginning, but I think to really see what's happening, this might be the right order. Okay.